Okay. Well, first of all, thank you, John, for your introduction. We'll kind of be building off of what John talked about. My name is Ruthy Rutherford, and I am one of John Rackovan's students at Miami University. And today I'm going to be talking about Miller indices. And for those wondering, this is a photo of William Howes Miller, who contributed to modern crystallography and for whom Miller indices are named after. So this is a TEM image of a fluoroapatite nanocrystal. And in this image, you can see the 3D atomic arrangement that shows a regular repeating plane of atoms within the structure of the crystal at an atomic scale. The planes of atoms in the structure control the flat faces that we see externally. And if the repeat is contiguous, you will have a symmetric crystal form externally. The faces that we see in crystals are parallel to planes within the atomic arrangement, which is also parallel to the lattice plane. And here you can see that parallel arrangement. By using Miller indices, we can describe the orientation of that plane of atoms relative to the crystallographic axes. They are a unique representation of any plane relative to the crystallographic axes. As John discussed earlier, this is a lattice structure, and in it we can define a plane, this blue plane for instance. We can talk about its orientation relative to the crystallographic axes using three numbers known, which can be represented by an HKL, and I'll talk about this a little bit later. Here you can see the crystallographic axes in the positive and negative X, Y, and Z directions. In those directions, we see the repeat of A, B, and C. So how do we determine the Miller indice now? Well, to start, we look at the relative A, B, and C units of repeat. Where the plane intersects the X, Y, and Z axes are known as the intercepts. So here we can see the intercepts of the plane along the X, Y, and Z axes in terms of the A, B, and C units of repeat. And in order to find the Miller indice, the first step is to find the intercept. The first intercept in the X direction is 1A. In the Y direction, the intercept would be 2B, and the Z direction, the intercept would be 2C, which all of them are plotted here. The next step is to then invert these intercepts. By doing this, we get 1 over 1, 1 over 2, and 1 over 2. Next, we multiply by the smallest number necessary to clear the fractions. In this case, that would be 2. So we multiply all of the inverted intercepts by 2. That gives us 2 over 1, 2 over 2, and 2 over 2. And this is also known as the 2, 1, 1. Notice that this is put in parentheses. There are other types of indices that are 3 numbers that can represent directions, forms, and points. However, when you see the parentheses, you know that you're looking at a Miller indice. The next step is to reduce your answer to lowest terms by dividing by the largest common factor. In the case of the 2, 1, 1, we already have it in lowest terms. So let's take the 2, 2, 6 for example. If you were to go through the steps 1 through 4, and got 226, this would not be the Miller indice because Miller indices are only found in lowest terms. Reducing the 226 would then give you the Miller indice of 113. Here we can actually see a crystal with a 113 face and its crystallographic axes. And this crystal is actually a hexagonal crystal, and I'm going to talk about how to find the Miller indice of that in just a few slides. So let's try this one together now. And for the rest of the slides, I'll be asking you guys questions that you can answer in the chat, and then Chris can let me know when you guys respond. So to start, we need the intercepts. So can anyone tell me how many units of A are there in the X direction?
Ruthy, oh, there we go.
I'll give you a hint. It's right here.
Yeah, seems like 4 is the most popular answer.
All
coming in.
right. That would be correct. It would be 4. Now, can anyone tell me how many of units in the B, of B in the y direction?
Seems like there's a array of answers, 2 or -2.
Yeah, so to clarify, this one would be -2, and the reason is, if you notice, you're going in the negative y direction. Over here would be the positive direction. So if it were here, you would get 2, but it is here, so the answer would be -2. And then last, can anyone tell me how many units of C in the z direction?
Seems like 2 again.
Correct. So now that we have the intercepts, the next step is to invert those intercepts. So can anyone tell me what that would be inverted, all 3 of them?
Yep, 1/4, -1/2, 1/2.
Yep. So then we get to multiply by the smallest number possible to clear the fraction. Can anyone tell me what that number would be? That is the number that you would multiply it by.
4 seems like.
Yep, 4 is the
Johann.
correct answer. So that would give us 4 over 4a, 4 over -2b, and 4 over 2c. And that, of course, then simplifies to 1, -2, 2. And this is already in lowest terms. However, something to note is we actually represent negative indices with what is called a bar. So we would actually call this indice the 1 bar 2, 2. Good job, everyone. So this is an example of when a face is parallel to the axes. So when finding the intercept in this case, we visualize this.
We've got another question from the Q&A.
Sure.
So how did we originally define the plane on that mineral? The plane that we just mathematically described using the Miller index.
How do we define that plane? Well, it would be defined, so
Ruthy,
how?
can I jump in here?
Sure.
Okay, that's a very good question when I figured that would come up. Before we had X-ray crystallography, we actually we used morphology to figure out what our axes and our repeats were. We don't have time to get into this, but you would choose the largest, most commonly observed face as a unit face, and then you would base the orientation of other faces relative to that. Once we have X-ray diffraction, we can figure out exactly what the orientation of the plane is relative to the lattice, and that's how these drawings that Ruthy is pulling up are created. But that takes a little bit of work to think about. So for the time being, we're going to use the X-ray determined orientation.
Thanks, John. Yes, there's a lot that goes with that, so you could have a whole conversation about how that's done. So we'll go back to this example of when a face is parallel to the axis. So when we find the intercepts in this case, we visualize this plane extending infinitely in the z direction, and that's just the case for this example. So let's try and find the intercepts. So in the x direction, we would have 3a, and in the y direction, it would be 1b. Can anyone tell me, though, what it would be in the z direction?
The infinity.
Yep, that's right. So now we would invert those intercepts, and that would give us 1 over 3a, 1 over 1b, And then what would C be?
Zero. From Johan's very quick here.
Yes, you guys have jumped ahead a little bit, but for now we will call it 1 over infinity. So then we would multiply by the smallest number possible to clear the fraction. So can anyone tell me what that number would be that we multiply it by?
So everybody's coming up with 3.
Okay, cool. So yes, that would then give us 3 over 3a, 3 over 1b, and 3 over infinity. And if some of you were confused why people were saying 0, when we simplify 3 over infinity or 1 over infinity, as you increase a denominator, a fraction becomes closer and closer to 0. So when infinity is the denominator, it's so big that it just simplifies to 0. And knowing this, we then know that the Miller indice would be the 130. So let's try it with this one now. Can anyone tell me what axes this plane is parallel to?
Say Z.
Yep, that's one of them.
And Y.
Yep. And just to help with the visualization of this one, it actually intercepts right here at the 2a, and then it's extending infinitely in the y and z direction. So, that being said, it's parallel to the y and z, and that gives us the intercepts of 2a, infinity b, and infinity c. So now can anyone tell me what it would be inverted?
One half 0 0 coming in.
Yep. Again, jumping ahead with the zeros, but yep, you are correct. So then what will we multiply these by?
2.
Yep.
Victoria and Douglas.
So that would give us 2 over 2a, 2 over infinity b, and 2 over infinity c. And then as you guys said, that then simplifies to 0. So that would give us the Miller indice of the 100. Good work, guys. So can anyone tell me now what the Miller indice for this beautiful fluorite face perpendicular to the x-axis would be, which in this case is this face here?
100.
Yep, and it's the example that we just went over. So good job. So now, using your understanding, can anyone take a guess as to what this face, HKL, might be? And it's perpendicular to the z-axis.
001.
Yep, that would be correct. It is the 001. And now let's try this face, which is kind of hard to see, but it would be over here perpendicular to y.
People are saying 001. Sorry, Douglas just said 010 finally. And George.
Yes, the 010 would be correct. This one right here would be the 001, and then this one right here would be the 010. Good job, guys. Caught on fast. So now everyone break out your pencils and paper, because I'm going to go ahead and let you try one on your own without any guidance. So here's our example, and I'll give you about 20 to 30 seconds to try and figure it out. Are there any questions in the chat so far, Chris?
Yeah, sorry, my Zoom is being very laggy right now. There's one that I guess we can talk about right now. I was typing an answer to, but someone asked if, so Miller indices were introduced before X-ray diffraction, which they were.
Yeah.
Commenting on that, trying to balance between also looking at the chat. But yeah, you're doing a great job, Ruthy.
Thanks, Chris. Okay. I will assume that you guys have pretty much worked through it. So
these are 211, Ruthy.
Awesome. That is correct. The answer is 211. And I'll just go through it really quickly. So the intercepts would be 1A, 2B, and 2C. Then we would invert them to get 1 over 1A, 1 over 2B, and 1 over 2C. Then we would multiply them by 2 to get 2 over 1A, 2 over 2B, and 2 over 2C. And then that would then simplify to the 211. Good work. So also, just to talk about it really quickly, so I introduced it to you guys before, the HKL, and it's just a variable representation, basically. So in this case, the 2 would be representative of the H, the 1 would be representative of the K, and the other one would then be representative of the L. Here's a garnet that shows an example of a 211 face, and it's like the one that we just looked at, and it also has a 110 face. So all of the crystal classes that we've looked at so far have been either monoclinic, triclinic, orthorhombic, tetragonal, or isometric. The hexagonal system, though, is unique in that it has a slightly different set of unique crystallographic axes. The other crystal systems follow the XYZ setup, while the hexagonal has axes in the X1, which is equal to X, X2, which is equal to Y, the Z direction, and X3, which is the new axes that we see in the hexagonal system. This is because the hexagonal system can be represented by 4 numbers in its Miller indice instead of 3 like our previous examples. So in the example that we looked at before with the 211, I mentioned how 2 is equivalent to H, 1 to K, and 1 to L. With the hexagonal system, since we have 4 numbers, we have a new letter I. So this would read 2, 1, bar 3, 1. I is actually equivalent to the sum of H plus K times -1. And this is important to note because in most publications, they only publish 3 Miller indices. So in this case, they would say the face 211 on the hexagonal crystal. Because you know it's a hexagonal crystal, you can sum H plus K and multiply it by -1 to find the I. However, it is important to distinguish that this only applies to the hexagonal system. The 211 face on an isometric crystal would not be the same as the 211 on a hexagonal crystal. Since the X direction is equivalent for X1, X2, and X3, then their repeat dimension is the same for all 3 of them. And we represent that with A. So now, let's try an example. So when looking at this example, imagine the Z-axis coming out of the screen towards you. The red lines represent the edge of the planes that we're showing, and we see an edge because it's parallel to the Z-axis. Also, it's important to note which direction is the negative and positive for each axis, in particular with the X3. See it going in the positive direction this way. Let's see. So we're going to look at the one on the left first. So first, find the intercepts. So can anyone tell me what the intercepts would be here?
That 221 or 2 to infinity. There are a few different answers here.
Okay.
2 bar 1. Well, I guess
So,
one would be the intercept.
so the answer in this case, remember you have 4 numbers. So you were correct in saying infinity, but to clarify, the infinity is not this I. Remember, this represents the H, the K, the I, and the L. So the infinity would be going in the Z direction towards you. But the one that I heard an incorrect answer for, I'm pretty sure, was the I direction, or the I in HKIL, which is the X3 direction. So in this case, it would actually be -1, because remember, you want to take into consideration that the X3 is positive in this direction, so it would actually be negative in this direction. So that means that the intercepts would be 2, 2, -1, infinity. So next, can anyone tell me what that would be inverted?
So yeah, 1/2, 1/2, -1, 0.
Okay, good job, guys. So now, then you would multiply these all by 2, and that gives you 2 over 2, 2 over 2, -2 over 1, and 2 over infinity. And then can anyone tell me what that would simplify to?
See, 1120.
Yeah, so don't forget,
R2, sorry.
thanks, Chris. So you would have the 1, 1 bar 2, 0. So one thing that you could do is, instead of finding the intercept for A3, you could also use the formula I equals -1 times the sum of H plus K. And that would give you the 1, 1, 0. And either way, you would get the same answer. However, in the hexagonal system, it can be very useful to show the 4 indices. And that can be seen in our next example on the right here. But just for the purpose of time, I'll just go ahead and give you guys the answer. And that would be 2 bar 1 bar 1 0, or the 2 bar 1 0. But in this case, the 2 is in the H position instead of the I position. And this would not be the case if this were not a hexagonal crystal. So it can be useful to use all 4 numbers as well. So this fluoroapatite on quartz is a hexagonal crystal. And here are its axes. And it shows a 2 bar 1 0 face, which is what we just went over, along with a 1 0 0 face and a 0 1 0 1 face. And that is where I'll end my presentation. I went a little bit over, but here's a lovely specimen to end. So yeah, thank you guys.
Great. Yeah, I knew this rock would make an appearance, John, but there's an interesting one in the Q&A for the crystallography team. So before X-ray diffraction was invented, how were the repeat units defined? And I guess a better way to phrase this question is, what was our understanding of crystallography kind of down to the atomic level before X-ray diffraction?
So very quickly, without getting into the details, that's what I had tried to explain before, and that is, you would take the most common and largest face present on crystals, and you'd have to look at a lot of them to do this. You choose one of them as an index face. You then draw your crystallographic axes based on symmetry relative to that, and then the indices would all be based on that as a reference for a reference in terms of intersecting X1, A, Y, 1B, and Z, 1C. So that would define what your repeats are, and then you would base all your other faces relative to that. And once we turned to X-ray crystallography, we learned that that wasn't always the case in terms of the repeats. An example of that is the 101 in calcite morphologically became the 104 morphologically, because in terms of the